The holy grail of investing in the financial markets is about producing results that are equal or better to the benchmark index with lower volatility or risk, the so-called risk-adjusted return. And if you look at the multi-trillion-dollar investing industry, there is a lot of phenomenal talent in that industry chasing these returns, chasing alpha, and trying to get to S&P 500 type of returns over the long term. And yet, about 85-90% of the funds fall short and are unable to even approximate S&P 500 type of returns, let alone do that with lower risk. And the vision of one individual, Jim Simmons, that some of you may have heard about, was to use the power of data and make a system so advanced that, as he put it, it would make money while he sleeps. That was his vision. And he's embarked on that vision 31 years ago, accumulated some of the brightest minds, physicists, mathematicians, I'm sure several people from Berkeley, and put together this team, and some of the most astounding results that you have ever heard was delivered by his fund over 30 years, where from 1988 to 2018, where most funds have struggled to do 8-10% annual compound growth rate. His fund compounded 66% a year, gross returns over 30 years without a single down year, after multiple bear markets and recessions over that time frame. And most interestingly, it met his goal of making money in his sleep, because it is entirely run by algorithms. All of the small team working in that fund are essentially tweaking these algorithms, but they don't place any real trades. All of the trading is done by these algorithms. And today, 2/3 of all the trading on the stock markets in the US have been taken over by algorithms. And many people, tens of thousands of people who earned 6- and 7-figure incomes are no longer employed in that industry. And so this is just a small, tiny window of the power of artificial intelligence and machine learning, because those are the techniques that these physicists and mathematicians used in their algorithms. And it is a self-learning system. It gets better every day. It consumes massive quantities of data from all the global markets and trades, on those global exchanges. And it's starting to affect people who are white-collared, high-paying jobs. And we are increasingly getting to a world where computers can now do better diagnostics on scans of cancer than radiologists can. And computers can do better assessment of the risks in insurance claim processing than human beings can, and certainly do it faster. And so artificial intelligence and machine learning is getting really advanced, and it's going to have profound impacts on society in the years ahead. And so the topic for today's discussion is really a fascinating one about how we will coexist with the world of tomorrow. And I think we are all in for a treat. I'm personally very interested in hearing what the panelists have to say. So ladies and gentlemen, welcome to Micron. We are really delighted to host you here this evening. Micron, as you saw in the video, is a company that's a world leader in memory and storage solutions. We are the second largest company in the US in the semiconductor field, behind Intel, and the fourth largest in the world. And we have, over the last 41 years, contributed 40,000 patents and innovations that have really fueled this industry. And as you know, memory and storage are at the heart of all the machine learning and AI of tomorrow, because that's where all the data resides. And we are very proud to work with all of the industry leaders to really foster the innovations that this technology will bring. But of course, it brings with it profound questions for our society. And I'll be really interested in seeing what the panel talks about in terms of how we address some of these challenges. So without further ado, I want to introduce Dean Sujay Lu to you. I know none of you require an introduction to her. I know Dean Sujay for some time, and her bio is incredibly impressive, and it'll take me the rest of this evening to just go through her bio in front of you, so I will not do that. But suffice to say, she has co-authored or authored over 500 publications, has more than 90 patents, is an IEEE fellow, is on the board of Intel, and a whole bunch more accomplishments that should certainly make all of us very proud to know her. So please welcome Sujay.
Thanks so much. Thank you, Sumit. Well, good evening, everyone, and welcome. It's my pleasure and my honor to welcome you all to this event. We're going to hear from some of the star faculty who are working on artificial intelligence and machine learning in just a few minutes. But I'd first like to take this opportunity to express deepest gratitude to Sumit and also the CEO, Sanjay Mehrotra of Micron Technology, who couldn't be with us here today, really to host us in this beautiful venue. I was told that we are the first party that you're hosting here in this new building, so it's nice to have that honor. So Micron Technology, I just wanted to acknowledge, not only has developed the world's leading memory chips to enable the AI revolution, but they've also done a lot to help cultivate the next generation of technology leaders. And so at UC Berkeley, Micron has been a strong supporter of various programs in the College of Engineering. And these include some summer bridge programs to prepare incoming freshmen and transfers for our rigorous engineering degree programs. So these are the prep and T-prep programs. Micron Technology also supports research experiences. It provides some funding to allow some of our undergraduate students to have research experiences. That's made possible through the Semiconductor Research Corporation, through the Joint University Microelectronics program, for which we are really grateful. Also, Micron has supported a program for middle school students, and I know there's some middle school students here. It's a program called Girls in Engineering, but it's really intended for all middle school students to learn about the field of engineering, because we really need the best and the brightest people to want to go create tomorrow's technologies that will transform our future. Now, tonight we wouldn't be here without the support of all of you in the audience. So I'd really like to express gratitude to the members of the Dean Society, alumni, parents, friends, and your guests for coming here and for your support that you've provided over the years. This program is designed really for you, to keep you informed of all the exciting things that are happening at Berkeley. I hope that you have had a chance to meet with our students to learn about the research they're doing. You'll hear directly from the professors for a while, but afterwards we'll have dessert, and then you get to talk with the students a little bit more. Now, Micron has been a strong supporter of research as well as education at Berkeley. So at Berkeley, we have the Berkeley Artificial Intelligence Research Lab, or the BEAR Lab, and Micron is one of the industrial supporters of that. And so it's especially appropriate that we're hosting this series of speakers and panel discussion to cover the concern that some of us have about AI becoming super intelligent, and what does that mean for human coexistence? And I think Micron Technology enabling the AI revolution, I think we all want to take responsibility that not only for innovating better technology, but also looking carefully at the ethical and societal implications of the technologies that we're developing. So this is something that's really important to us at Berkeley, because we really want to educate leaders, create new technologies that will be beneficial for society. So today, hopefully you'll hear about what we're doing not only to advance technology, but also to make sure that this technology will be for the benefit of humankind. So without further ado, let me first invite Professor Stuart Russell to come to the stage. He's going to give us some background to understand this topic of why we might want to be worried about intelligent machines. super intelligent machines. And so he has a long list of accolades, so this is why I have notes here. Professor Russell holds an endowed chair, the Smith-Zadeh Chair of Electrical Engineering and Computer Sciences. He's a full professor in the EECS department at Berkeley. Now, he's world famous for writing the book on artificial intelligence, literally. His textbook, which he co-authored with Peter Norvig, formerly of Google, is used by, you might want to guess, over 1,400 universities worldwide. There's over 1,000 universities in 128 countries. I assume that they're in different languages too. Yes. So he's addressed the United Nations on several occasions concerning the threat posed by autonomous weapons. You might have seen his TED Talk on that topic. And he's earned many honors, and including the Computers and Thought Award, which is the premier research award in AI. And he's also the founder of the Center for Human-Compatible Artificial Intelligence at UC Berkeley. And actually, Professors Anka Dragan and Peter Abil are members of that center. So Stuart more recently received the Andrew Carnegie Fellowship, which is one of the most prestigious awards in the social sciences and humanities, right? Because there's tremendous social impact of AI. And actually, he just he actually solely authored a new book. I don't have a copy here, but the publisher generously has provided complimentary copies of Professor Stuart Russell's new book, and each of you can pick up a new copy. I think he might be willing to sign it for you if you are inclined. So please don't forget to pick up your But you have to ask him a question. No, I'm just kidding. Just kidding. Okay. So he's going to give us a brief 10 to 15 minute presentation, and afterwards we'll have a panel discussion. So please take it away, Stuart.
Thank you very much, Sujay. So the question of how we can coexist with increasingly intelligent machines is actually a very old one. So some people point to Asimov's story in 1942, where he introduced his 3 laws of robotics as the beginning of concern about how to make AI systems safe, how to have a beneficial coexistence. It turns out actually that Aristotle also wrote about this question. And it's quite amazing to think that in 340 BC, he was writing about automated machines and the effect they would have on employment. So he was literally writing about technological unemployment. He said, look, if we have musical instruments that play themselves, and if we have weaving machines that weave the cloth by themselves, then we're going to have a massive unemployment problem among all the slaves. So what are we going to do with them? You know, so things don't change that much. Okay, so what did Asimov say? Asimov said, a robot may not injure a human being or through inaction allow a human being to come to harm. So the EU Parliament actually debated enshrining Asimov's laws in legislation, right? That this would not just be a science fiction story, this would actually be law in the European Union. Fortunately, they didn't go that far because there are some very clear problems with Asimov's laws. Probably the first one is that it completely ignores uncertainty. So you might be harmed by a photon that comes from the sun and lands on one of your skin cells and just happens to be the photon that breaks a DNA strand and initiates a melanoma. And so the robot has to run around with an umbrella over your head to make sure that none of those photons hit you. If you ask it to drive you to the airport, it says no, because you might get into a car crash on the way to the airport, so I'm not driving you, we have to stay in the garage. Right? So we now understand in AI that actually uncertainty is ubiquitous and unavoidable, and you are always making trade-offs. So you can't prevent all harms. You have to make judicious choices. Right? If you overtake someone on the freeway, they might sideswipe you into the central reservation and you'd be toast. Right? But that's a risk you take. You can't prevent that from happening. You just hope it's a low probability event. So that's the first thing. So we could try to fix up Asimov's laws to talk about expected benefits and expected harms. But the other problem is that there's no explication of what harm actually means, right? And without a definition of harm, there's nothing the robot can really do with this law. Obviously, what harm means actually varies according to different individuals. So what might be a harm to one person actually would be, something welcome to another person. And obviously, it varies across cultures. You have to think about harm to future generations, as well as the present generation. How do you trade off those harms? So there's a lot of completely unresolved issues here. So you might say, okay, let's think about safety of AI systems in terms of meeting their formal specification, right? That's often what we mean in engineering by safety, is that we write down the specification and we show by some mathematical techniques that it meets this formal specification, and then it's okay. And so this is actually how things have proceeded in AI, right? The standard model of AI is you specify the objective for the machine figures out how to optimize it and goes ahead and optimizes it. But this is not a very good engineering model, it turns out. So just to give you an example, right? If you look at what happened in social media over the last few years, there are machine learning algorithms that are optimizing a fixed objective, and they do it very well. They meet their specification. They optimize click-through. Now, when the social media platforms, who I won't name, we don't have to name and shame them, but you can guess who I'm talking about. So when they wrote these algorithms, I think what they thought was, oh, the algorithms will learn what people want. And that's good, because they don't waste their time sending them videos or news stories that they're not interested in. But that isn't what happened, right? The way to optimize click-through, if you're one of these learning algorithms, is actually to discover how to manipulate people to be more predictable. Because the more predictable you are, the easier it is to monetize you. And so they learned to gradually move people through the political spectrum to the points where they were most predictable. And it seems to be the case that the extremes of the political spectrum are where you are more predictable. You become a voracious and very predictable consumer of certain types of content. And so these fairly simple algorithms, by pursuing an incorrect objective and being deployed on platforms to billions of people for hours every day, have had a massive collateral damage effect on the world. And so this is why this engineering model is a bad idea, that we don't know how to specify the objectives completely and correctly. Okay? This is not a new theme. Again, going back to the ancient Greeks, right? So King Midas specified his objective. I want everything I touch to turn to gold. And the gods, in this case, rather than the AI system, implemented this correctly. So they met the objective, the specification. And then, of course, his food and his drink and his family all turned to gold. And he dies in misery and starvation. So this is an object lesson that pretty much every human culture has stories like this, right? The lamp, you rub the lamp, you get 3 wishes. What's the 3rd wish? Please undo the first 2 wishes because I ruined everything, right? So we know this story already. So my conclusion is that we can't fix this by improving our software engineering practices, by having software walkthroughs or formal verification. The problem is that the whole paradigm itself is the wrong one. So how do we get in this mess, right? I think it was sort of by accident. We, in the 1940s and 1950s, right? So we had some computers finally. Aristotle didn't have any. Otherwise, he would have been an AI researcher, I'm quite sure. Well, he would have needed electricity as well. But anyway, so we finally got the electricity and the computers in the same place. in the 1940s, and people like Alan Turing started thinking about using them to make intelligent machines. And so the question is, if you want to make an intelligent machine, what does intelligent mean? Well, they looked to the definition of intelligence that was already prevalent at the time. Human intelligence, the definition was developed in philosophy and in economics around this notion of rational behavior, right? That acting in a way that can be expected to achieve our objectives. This is what we mean by human intelligence. And they simply transliterated that to the machines, right? This is what we mean by intelligent machine. Their actions can be expected to achieve their objectives. And of course, unlike humans, they don't come with objectives, so we have to plug in the objectives. And every chapter of the AI textbook assumes, I now understand incorrectly, assumes that the objective is fixed and known. And this is not just AI, right? So control theory minimizes a cost function, and you assume that the cost function is fixed and known. Statistics minimizes a loss function. Operations research maximizes a reward function. Economics maximizes GDP or quarterly profit or some welfare function. So all of these disciplines are, I would say, making the same mistake. And in economics, they sort of recognize this, right? They say, well, we know that GDP is not the right thing to optimize because it doesn't take into account inequality or externalities like pollution, depletion of natural resources are all ignored in GDP, but they can't get away from this measure. So my view is we have to get rid of this notion. It's the wrong notion for what we want. We don't want machines that are intelligent in this sense, because when they have an objective that isn't complete and correct with respect to human preferences, which are extraordinarily rich, that stretch it far into the future, it's impossible to capture all of those and write them down and be sure that you've done so. So what we want instead is machines that are beneficial to us, right? So that means that their actions can be expected to achieve our objectives. Okay? So it's just changing one word, right, from there to our. And obviously, if we can do that, then we're home free, right? We have machines that are helping us. They're not pursuing the wrong objective. They're pursuing our objectives. Obviously, the problem is that our objectives are in us. And we may not even have access to them, let alone the machines. Okay? So this actually sets up a completely new kind of decision-making problem. Decision-making where you're pursuing an objective of some other entity which you don't know. Okay? And the question is, how do you formulate that? How do you solve that? How do the resulting systems behave? And so that's what we're working on at the center at Berkeley. So in honor of Isaac Asimov, I wrote this down in the form of 3 principles. Okay, so the robot's goal, its constitutional design, if you like, is that it should satisfy human preferences. And again, these are preferences not just what kind of pizza do you like, but what future do you want? What do you want the future to be like? And the main difference here, the second principle, the robot is uncertain about what those preferences are. The third principle is basically a way of connecting human preferences, which are, as it were, invisible, to some form of external evidence that the robot can use to learn more about the preferences. And that evidence is our behavior, right? The assumption is that our preferences influence the way we behave. And therefore, by observing the behavior, you can infer something about the underlying preferences. And clearly, the connection between what we want and what we do is a complicated one. We are not perfectly rational. We suffer from myopia, weakness of will, emotional reactions, all kinds of reasons that our behavior doesn't strictly match our preferences. And so the robots will have to, in some sense, be kind of inverse psychologists. Now, you can actually turn this into a mathematical problem. And this is essential, right? when we build these machines, they are machines that are solving some well-defined mathematical problem. And if you set up the problem correctly, the solutions will be something that you want. And so the problem, we call it the assistance game, where the human has some preferences. I wrote U for utility. And then the robot's goal is to maximize that function U. Doesn't know what it is, but it has some prior probability distribution over what those preferences are. Okay. So I'm not going to go into any, that's as technical as it gets, right? So no more technical detail. But when we formulate these and we solve them, right? So we solve, as it were, the machine half, and we can also look at what the human half of this problem looks like. The machines end up deferring to the human being, because the human being is the source of the preference information. The human being, in some sense, knows better what they want than the robot does. So, for example, if the robot comes, it has some notion of what we want. For example, it might know that we want to restore carbon dioxide levels to the way they used to be, so our climate gets back in balance. And it comes up with a plan which involves turning the oceans into sulfuric acid. Now, it doesn't know whether we like the oceans to be sulfuric acid or not, right? It's uncertain about our preferences for ocean pH. And so rather than just go ahead and do it, right, which the old style of AI system would do, because it just has the objective of restoring CO2, right, it would ask permission because it knows that it doesn't know our preferences for that part of the world. It will also allow itself to be switched off. Again, the old style AI system would never allow itself to be switched off because that would guarantee failure in achieving the objective, right? But here, the objective is simply satisfy human preferences. If the human wants to switch me off, it's because I'm doing something to violate those preferences. And so I'm happy to be switched off to make sure that that doesn't happen. So the important point here is the desire, or the willingness to be switched off, I should say, comes directly from uncertainty about preferences. As soon as I am certain about human preferences, I no longer will allow myself to be switched off. And so there's this direct relationship between AI systems being safe and controllable and AI systems having uncertainty about human preferences. So another way of putting the same point is in the old model, right, the smarter the AI system, the worse it is for humanity because it's pursuing the wrong objective. Whereas in the new model, the smarter the AI system, the better it is for humanity because it's better at learning what we actually want as well as achieving it. Now, your brains are all whirring away and coming up with objections or questions about how is this all going to work and so on. So I'll just save you the trouble and point out two of them. So one of them is obviously that there's more than one human, right? So we all have different preferences. That's fine. Facebook already has 2.5 billion preference models for humans, so we can easily stretch to 7.7 billion. That's not really the issue. But there are some tricky things. Obviously, this is why we have the social sciences in the first place, right? And why we have moral philosophy. If there was only one human being on Earth, we wouldn't have social sciences and we wouldn't have moral philosophy. So it's all about how do you act on behalf of multiple people? And then you get questions like, well, what about all the future people who haven't been born yet? And what if there are many more of those than there are of us? How do you make decisions on that basis? How do you make decisions that might change the number of people who exist, as the Chinese government did with their one-child policy? That actually, at a stroke, wiped out 500 million people who would otherwise have lived. Was that a good thing or not? Right? Philosophers still argue about these questions, but AI systems need answers if we're going to get this right. Another important point, as I mentioned, humans are not rational. So in order to understand our preferences by observing our behavior, we have to invert that somewhat irrational, complicated, biologically engineered cognitive process in order to get at the underlying preferences. And there are lots of issues here about emotion, about complexity. Probably the most tricky one is is plasticity of preferences, right? The fact that we can modify the preferences of people by changing the environment that they operate in. And you don't want the AI system to satisfy your preferences by modifying them to be easier to satisfy, right? We already have politicians to do that, and we don't need AI systems to be doing that too. So, to summarize, we're in a very exciting time for AI right now. I didn't have time to talk about the upside of AI, but it is enormous. In the book, I do a little back-of-the-envelope calculation. What's the cash value of achieving human-level AI? And it comes to between 10 and 20 quadrillion dollars. So you might not even know what a quadrillion dollars is, so that's 10 and 20,000 trillion dollars. So the investment amounts that are blowing everybody away right now, like the Chinese government talking about $150 billion investment in AI, are absolutely minuscule compared to the economic value of what we're going to achieve. But we don't get any value if we don't control the risks. And the nuclear industry found that out the hard way. They had Chernobyl, and Chernobyl decimated the nuclear industry, and we did not get the benefits of nuclear power as a result. So you cannot get the benefits of powerful technologies without ensuring that you understand and mitigate all of the risks. And I would say right now, we are definitely not prepared for success. If general purpose superintelligent AI happened tomorrow, it would be a really, really bad thing because we do not know how to control it, right? All we have at the moment are a few ideas like the ones that I told you, but we don't yet have fully worked out algorithms, technologies, and deployed systems. So we have a long way to go. So we need to replace the standard model for AI. We need to rewrite every chapter of the textbook, which means developing the new algorithms, the new frameworks, the new formalisms, and then the new products from that basis. I believe this is possible. And it's also desirable. There's a very strong economic incentive to do it this way because your products will be beneficial if they're designed this way. And your domestic robots won't cook the cat for dinner because they will understand that you might have some emotional value attached to the cat, and they should definitely ask permission first before doing that, right? Now, there are a few other problems I don't have time to talk about. So misuse, right? What we call the Dr. Evil problem. Misuse is clearly a problem already with malware and cybercrime. And we're doing such a great job of controlling that that we'll easily be able to manage the control of superintelligent AI. And then overuse. So if you've seen Wall-E, there's the problem of overuse, right? That you use too much AI so that basically we turn over the management of our civilization to machines because it's so much easier. It's so hard to learn all that stuff, go to school, take all those exams, get those B's and C's, and it just sucks. So it's so much easier just to not do it, right? But that's unfortunately an irreversible process. So we need to be very careful about that. And we don't have any solutions for these problems, and they're really not technological. They are problems for everyone to solve. So with that, I will say thank you. And here's a picture of the book. I think this is the UK edition, actually. So the one outside is probably the blue one. And if you're interested, all of what I said is actually explained in more depth in the book. So thank you very much.
Thanks very much, Stuart, for that really compelling introduction, thought-provoking to the discussion this evening. I'm tempted to ask you why you chose that cover image, but we'll leave that for later. Now I'd like to invite our expert panelists to the stage, and I will introduce them one by one. Peter Abbeel. Professor Peter Abbeel is from the Department of Electrical Engineering and Computer Sciences. He's a co-director of the Berkeley AI Research Lab, and he's also director of the Robot Learning Lab at UC Berkeley. Now, his work in AI and robot learning has been featured not only in technical publications, but in top-tier media outlets such as the New York Times, Wall Street Journal, Wired, and on National Public Radio. He shares his spotlight with BRET, which is acronym for the Berkeley Robot for the Elimination of Tedious Tasks. And Brett first rose to fame in 2010 by folding towels. And Brett can do much more today, as Peter probably will explain to you soon. Next, I'd like to invite Professor Anka Dragan to the stage. She's also in the Department of Electrical Engineering and Computer Sciences. She's the head of the Interactive Autonomy and Collaborative Technologies, or INTERACT lab at UC Berkeley. Her lab focuses on algorithms for human-robot interaction across a range of applications, from assistive robotics to manufacturing to driverless cars. And her goal is to enable robots to work with, around, and in support of people. And finally, Steve Pawlowski. He's the Vice President for Advanced Computing Solutions at Micron Technology. And in his role, he's responsible for helping Micron further develop and define memory solutions for high-performance computing. He's led efforts at Micron to create a deep learning accelerator platform, which is used to understand customers' workloads for a range of applications, from early cancer detection to subatomic particle interactions, I guess, for scientific discovery. Now, Steve joined Micron after 31 years at Intel Corporation, where he became a senior fellow, and he was chief technology officer of the data center and connected systems group. Maybe I'll ask Stuart, please make yourself comfortable on the stage as well. And maybe we'll give each of the new panelists just a few minutes to introduce their research to you, and then I'll start with some questions. Peter?
Hi, good evening, everyone. I'm Peter Abil, and tried to make robots learn. So the motivation here is that if you look at existing robotics that's functional today in, let's say, car factories and other automation environments, it's really based on repeated motion. And my belief is that in the future, most of the value robots are going to bring is going to be through things that they have to learn rather than can be hard-coded to do. And so my lab is working on that in the context of household robots, maybe organizing laundry, also in the context of more industrial applications. And it doesn't have to be a manipulation robot. It could be a driving robot. It could be a flying robot. It's kind of the beauty of today's AI. I would say that the underpinnings are very, very general and apply across many domains with the same foundations powering all of them.
Okay. Hi, everyone. I'm Anka Dragan, and I work in human-robot interaction. So broadly speaking, my lab is motivated by this observation that we've been improving robot and AI capability in general, and that's really great, but that's sort of lacking in two fundamental ways. One of the ways is that improving capability is awesome, except that improving a robot's capability to do something on its own doesn't mean that you improve the robot's capability to do something in coexistence with a person. So if you look at this notion of coexistence, it should ideally mean that if my personal robot is cooking a meal for me, I don't have to leave the kitchen because the robot doesn't know how to deal with me being there. And it turns out that when we make these robots, we want them to operate in these human environments in coordination and collaboration with us. And autonomous cars are definitely one of these examples, right? If all we cared about is autonomous cars being capable in isolation, they would drive on empty roads, and we'd be done with that years ago. What's really hard about autonomous cars is that there are these pesky humans around that you need to coordinate with, negotiate, merging on highways and intersections, and so on. So I think that's going from capability in isolation to capability in coexistence with people is really, really tricky. The other fundamental challenge is what Stuart was talking about, that capability for a specified task is one thing, capability for the correct task is a very different thing, because it requires also figuring out what the correct task actually is. What do people want these machines to be doing? And so in collaboration with Peter and Stuart, we're working on things like these irrationalities that people have, right? How coming up with a model that relates human behavior to human preferences, what they actually want, because people aren't optimal, and yet we have to figure out what they want anyway. And so we look a lot at how you might be able to model these things, how you might be able to model irrationalities. And it turns out that we're actually more rational than we think. We're just rational usually under the wrong assumptions, under the wrong time horizons, and so on. And so there's hope to this problem. And maybe I'll stop there and let Steven talk about what he does.
Wow. That's impressive. My name's Steve Pawlowski. I've been in the industry 37 years now, and I kind of wished I was just getting started because the opportunities are about like they were when I first started, before even the PC was something of interest. I came to Micron because at Intel I was running the exascale computing initiative to get to the first machine that can do 10 to the 18 floating point operations per second. Realized that was kind of a meaningless number because when you really took a look at the problem set, memory and storage were the biggest issue. And it was really, we were focused on computing, and the real, when you take these machines and you do, the muscle benchmark and say, I've got the fastest machine in the world, they're roughly about 1 or 2% efficient on the real problems that science cares about. So you're burning a lot of energy and you're getting very little value out of them. And as the data centers are consuming up to 2% of the world's energy today, and is projected to go up to 5% within the next 5 to 6 years, we needed to find a way to essentially, instead of bringing data to compute, bring the compute to data, and so actually change the computing paradigm. It's very difficult to do that with a standard computing model, but the opportunity that AI brings is that we actually don't have a software paradigm where people have been writing code for 40 years. And we have the opportunity to actually look at new structures and look for more optimal solutions. But that'll bring a bigger problem. The PCs that are being used today were designed and they were first architected in 1978, and nobody thought they'd be used in the way they're used today. And nobody thought that they would be exploited the way they are today. And so, I've used the analogy of we've just been sticking our finger in a dam trying to keep the thing from, as leaks start to spring out, trying to fix these security problems. And the unfortunate thing is they get fixed, but the person who fixed them goes on and does something else. A new person comes in and says, boy, that was a dumb idea, pulls it out, and you can have the same vulnerability that continues to show up over and over again. So the opportunity we have is a different computing paradigm, one that's memory and storage centric, and we have to fix it, get it right the first time. It doesn't mean we're not going to have problems, but we got to get it right the first time.
Great. Thank you very much for those introductions. So I'll ask just one question of each of the panelists and then hand it over to the audience just to get them warmed up for you. Maybe I'll start with Stuart. So you were suggesting that AI systems could figure out the right human beneficial objectives by observing human behavior, but we all know humans are not always rational in their behavior. So what gives you hope that automated systems can actually figure out the beneficial objectives just by watching how humans behave?
So one reason for hope is that we figure out each other's preferences in order to coexist and cooperate with each other. And I think, in fact, it's quite likely. So people in neuroscience and in AI used to think that all of our preferences come from our biology, right? Because we have a built-in reward system, a dopamine system, and evolution wants us to reproduce. And so somehow all of our preferences must come from that sort of original goal. And but it turns out, and this is sort of obvious to anyone in retrospect, that actually, no, they come from our culture, from our peers, from our parents. We have a built-in way of explaining the behavior of others in terms of inferring preferences. What is it that my parents want? What is it that my culture wants? What does my culture honor and respect, and so on and so forth? So we actually absorb these from our culture. And so the preference systems, for example, the preference system in Tibet, the most honored status is to be a monk who never reproduces, right? So how could that be explained evolution, just in terms of straightforward evolution? So our preferences, our cultural preferences are pretty much an autonomous system from our biology. And so it's a process of learning and internalizing preferences from each other. So there's clear evidence that it can be done, that our behavior is not so opaque that each generation sort of completely reinvents human preferences from scratch. And there's also a vast amount of evidence. So it's not just your PC or your phone watching you. It's all the PCs and phones watching everybody, plus the entire record of human history. So everything that's written down is really about people doing things. So you go back to the earliest writing, the clay tablets, which are incredibly boring, it turns out, right? You hope that, oh my goodness, this earliest writing is going to contain the seeds of human culture and civilization. No, it's Joe sold 40 camels to Mary in return for 300 bushels of corn, right? And then Dave sold 22 camels for I mean, it's really boring, but it tells you something about human preferences, right? In particular, it tells you how much people value camels versus corn and so on and so forth. And you see, right, some of the first ever letters that are written are people complaining about the poor quality of copper ingots that they got in return for their camels or whatever it is, right? And sort of asking for their money back. So, so things haven't changed much. But all of this is raw material that provides evidence. And also, you know, finally, just the last point is our preference structures actually have a great deal in common. So people always harp on about, oh, you know, there's enormous gulfs between cultures. But actually, the things we really care about, you know, our children, our health, shelter, food, well-being, and so on, those are universal. Friendship, respect. These are things that everyone on Earth cares about a great deal. And so if machines get most of that stuff right, then we're in good shape.
All right. I guess that's music to Micron Technology's ears. We want to just make use of all the information from the beginning of mankind over history, right? We need lots more memory.
Yep.
That's great. All right, Peter. So I know that you know, from your research, you've been making AI real for like physical systems, and today most of the AI systems, like for social media and so on, are in the cyber world, right? Software. But I know with your research, you really would like to have AI come to bear, be used like for physical systems. So what are some of the challenges for really implementing AI in the real physical world versus just, you know, online social media and so on?
It's a lot more challenging. So if you think about a lot of things you see in the news and you see maybe, I don't know, maybe some people saw OpenAI's Rubik's Cube and it's like very cool, but then you read the details, it's like 20% success rate. And so the reliability you need to achieve to do a cool demo that makes it into the news versus the reliability that you need in a factory or warehouse is just completely different. Any real world physical deployment requires a lot more reliability. If you just think about, let's say, imagine a robot and it's working in a factory and maybe that station needs to do 500 operations per hour. And now you say, okay, well, I look at research papers. This paper has 80% accuracy, pretty good. Oh, this one, maybe one paper somewhere is 90% on something. Say, okay, 90%, that sounds pretty good. But 90%, 500 operations per hour, you fail 50 times per hour. Now, someone has to come in and fix those failures. And actually then, that actually takes more time to fix a fail than just do the job. And now, what I've seen in practice, sometimes there's a robot and there's two people fixing what the robot's doing together, one robot and two people, the work of one person. And so it doesn't make total sense, but there's a spirit of it. They want to get into the future, and they want that robot to help out, but for now it requires still two people to fix it up. And that'll happen even when you have 95, 99% success rate with your robot. And if you look at any research paper, any demo that makes it in the news, you'll see that the success rates are a lot lower. And so I think that gap is really difficult to bridge, and that's where a lot of interesting challenges are going forward if you want to bring AI into the physical world, do physical things. Most extreme, of course, is self-driving, where you need many, many nines of reliability, because otherwise, well, the worst case is you kill someone. With a robot, the worst case is just it damages some goods it was producing. It's not that bad, but it's just costly. But even there, the number of nines you need is very high. And so a lot of what I like to think about these days is, how do we go from kind of a typical research mindset is 0 to 1, or maybe after 70%, move on to the next problem? How do we go from that to something that can go many nines of reliability and really create value in physical systems?
That's great. So Anka, you develop systems specifically to work with people, to either assist them or to collaborate with them. What are the differences and challenges, and which one's harder? To get robots to assist people or to collaborate with them? Let's say, like to manufacture?
Right, I don't know which one's harder. They're both hard. The one where you just have to coexist with people and do your own thing, like we do for autonomous cars, is hard because it falls into this formulation that we refer to as a general sum game. So that means that the car has its objective, the people around have their own objectives, and you're not collaborating, not working together. And so what's challenging about this is that in some places you'll be incentivized to kind of work as a team. So when we drive next to each other, we're both pretty interested in not colliding with each other, and we'll take actions that relate to that. When you're trying to get home real fast, because I don't know, something's happening, and you're trying to merge because a robot is frying your cat. It's a little bit adversarial. There's a little bit of competition there because, yes, we want to stay away from each other, but I want to merge in front of you. I don't want to wait for you to go and for the next guy to go and for the next guy to go and then finally make it in there. And so I want everyone to be safe. I want you to get home too, but I want me to get home a little more. And so...
Which is why we need autonomous cars.
But the autonomous cars will have the same thing, right? So it's this kind of weird collaboration competition where you have to anticipate what people want to do, but you also have to realize that what you're doing has an effect, has a bearing on what they actually end up deciding to do. Like if I just merge in front of someone, they'll slow down to let me in because they don't want to collide with me. That's in their best interest. But they might actually accelerate to make sure that they push me out of the way. All of those happen in sort of real world coordination. And then collaboration is hard sort of for similar reasons. There's a lot of needing to anticipate what the person is going to do and so on, but it's aided by the fact that we're really on the same team together, and I'm very incentivized to help you to make things easier for you. But the challenge is what Stuart was talking about, is that when I'm collaborating, I need to help you, but what am I helping you with? What do you want, right? What is the thing that I'm trying to help you with? So you have to work together with the person and read into all these different types of signals. It turns out people leak a lot of information about what they want, but you just have to be able to capitalize on that information and make sense of it and in order to learn their preferences.
Great. And finally, Steve, you mentioned that, like with the microchip industry, we see today a lot of security issues. As AI systems become more and more capable, how do we make sure that they're designed to be non-exploitable, or just to make it hard for them to be exploited for bad rather than for good?
Yeah, that's a great question. It kind of reminds me of a story back in the 486 days. We'd been shipping the processor for some time, and this one simulation expert came to me and said, "You've got a major bug in your design. We've got to stop all shipments of these PCs." And I said, "We've been shipping them for over a year and a half. What's the issue here?" And so he said, "Well, the model's telling me it's wrong." So he took me to the simulator, showed me the scenario. I said, "Processor cannot do that. I know for a fact the processor can't do that. You got to stop it. The model says this is what's going on. You don't know what the processor's doing. I don't know what the processor's doing. The model does." So we called the model guy that put it together and said, "Why did you think the thing could do this?" And he said, "We didn't know. We couldn't understand the specs, so we just put something in. Didn't expect it to come up with that." The problem was this individual trusted the results of the machine so much that he was willing to challenge the people that had a little more experience on it and say that you don't know. I really worry that we're getting that way with AI, and we're certainly going to be that with an autonomous car, because if you get in and there isn't a steering wheel or any way to stop it, you're really trusting that those machines can actually do the work they're really supposed to do. The advantage we have is, unlike a microprocessor, which is really a complex machine that is just added over time, AI machines, they talk about these 1,000 processor, 1,000 core systems. They're very simple devices in terms of the type of compute. And it's easier to find vulnerabilities in complex devices than it is in simple devices. But the last example I'll leave is I really worry about how much we trust the data. I was at a conversation with the Joint AI Task Force for the Department of Defense. And their chief advisor was showing me how they could without camouflaging an entire armored vehicle, they could use just a little spot. And if they moved it around to the vehicle to certain points, the machine couldn't tell that it was an armored vehicle, which it was trained to be able to do. So, being able to make sure that these machines are fairly robust and hackers will be able to understand the algorithm, they'll play around and find ways to thwart these machines. And that's the thing that worries me, is because you've got to trust something. If you're not trusting the machine, you can't trust the data. What are you going to trust?
Very interesting. That reminds me, just yesterday, some students at Berkeley were presenting a project where they come up with different ways to trick facial surveillance systems, so that if you don't want to be recognized by surveillance systems, you can. There are different ways you can do that. So, yeah, that's one way that people can exploit AI systems. And we're training the students how to do that, I guess. All right, at this point, let me hand it over to the audience. I think hopefully some of the discussion tonight has provoked some very interesting questions out there.
Hello. This has been a wonderful talk. I really appreciate it. So I'm going to mention a real-world issue that being a grandpa facing and trying to figure out what should I make suggestions to the elementary school district, which is not a bad district to begin with. My oldest grandson is going to move forward into 3rd grade soon, I hope. The question here is a lot of parents of that particular elementary school discuss something like, should we start teaching Python to the 3rd grader, and ever since then continue to advance forward. And there's only one question. The people we would like to trust to teach Python to a 3rd grade or 4th grader, or even more advanced, might have been employed by the high-tech industry, and the teacher filling into that kind of position have been underpaid, overabused, overused, blah, and blah. So I've been thinking about, since we have the world's wisdom right here in the panel, why don't we just set up a grant, getting a few PhD students set up to work on designing a robot? And that will be the best candidate to teach elementary school students Python.
Stuart?
Or you can tell me that this is just, completely out of a world thinking.
Well, no, it's actually, if you think it's a problem in San Jose, it's a far bigger problem in Chad or Mali or Central African Republic, where they can't afford any teachers at all. So kids are lucky if they get a couple of years of schooling. And so the AI community, among many other beneficial projects in support of the United Nations Sustainable Development Goals, is working very hard on AI tutoring systems that can actually teach any child in any country in the world to read and write and do elementary mathematics. The problem has been up to now twofold. One is the AI systems don't actually understand the content of what they're teaching. So they can regurgitate little demonstrations or little pieces of lecture or video, whatever it is. But they don't understand the content. The second thing is they don't share a communication language with the pupil, right? Because they don't really, and so you can't ask these tutors questions. So it would be like me trying to teach string theory in Laotian, which I don't speak, and string theory I don't understand. Right? So I wouldn't be much good at that, and that's sort of the position that we're putting the AI systems in. But two things are happening. One is that speech recognition now has advanced to the point where the system can communicate with pupils who are not yet literate. Right? And that's always been a big problem with using a computer. If you can't read and the thing only has a display, well, it doesn't help. You can't learn to read if you, from a computer that only has a display. But now that it has speech communication, you can teach kids to read. And pilots have shown that this is actually quite successful. So the X Prize, there was the Global Learning X Prize recently, and the two winners, one is a group actually called Kit Kit School, which is from Berkeley. So one of Randy Katz's old PhD students and his wife set up a small company, and they have a very successful product. On the question of programming, I mean, so there's two parts to this, right? So I actually think that programming is something that is excellent mental training and a very useful piece of fundamental understanding, because we spend a lot of time teaching arithmetic and algebra and so on, but what's the most powerful piece of mathematics ever invented? It's the Turing machine, right? So it's machines and programs. It's sort of like two pieces of mathematics. You put them together, and you completely revolutionize the world. Math departments around the world never recognized that this was mathematics. They think of computers as something that people, not even white coats, people in brown coats are the people who get computers to work. And so mathematics completely pushed computing out, and the engineering departments ended up taking it over, and in some sense taking over the world. So it's absolutely essential, I think, that these fundamental ideas be known to students from an early age, partly because it's how the world they live in works. But there's a second issue. I'm sorry, I'm going on a bit. But that's what happens when you write a book, right? You then. So the second issue is another really important one, right? What should we be teaching all our children? And what careers in the long run are they going to have? And I don't think that we should teach our small kids Python so that they can have jobs as computer programmers and data scientists when they grow up. Because those, at least most of those jobs, are fairly easy to automate. And in any case, those jobs, right, at most the world needs maybe 10 million data scientists. They're not going to replace the 2 or 3 billion jobs that Peter's and Anka's robots are going to take away.
Wow.
Right? So you have to ask, what are people going to be doing? And economists now consider this to be the biggest threat facing the world, at least in economic terms. What are people going to be doing when machines are doing almost everything that we currently think of as work? And let's face it, we've been using humans as robots for about 10,000 years. So since the end of the hunter-gatherer period, most people have been used as robots, doing repetitive, boring work that doesn't really access any of their human capacities. And that period's coming to an end. But we have to find what is the next period. And it's inevitable that the next period, what humans will be doing is functions that involve personal interaction, that involve one person making another person's life better through personal interaction. But right now, those jobs are low status, mostly low pay, because we don't have the science and engineering of how to do it properly. Right? We've put trillions of dollars into the science and engineering of networks and cell phones, which have raised the suicide rate and so on. But the science and engineering of how a person can help another person have a better life, whether through inspiration or coaching or teaching or just friendship, whatever it might be, is rudimentary. And that's why those kinds of professions like childcare, elder care, are very low paid, because they don't work very well. Right? They don't work very well because we don't have the science and engineering of how to do it properly. And if we did, then there would be billions of highly paid jobs because everyone would want those services. So that's, I think, what governments have to be thinking about. And it takes decades to make that, to change the direction of the ship of our education and science system.
All right.
Professor Russell, with regard to the Asimov first law in the standard model of AI. Again, with respect to the second statement that focuses on what AI should do, doesn't that statement suffer from the uncertainty of the choice of a person the AI is supposed to protect from doing harm to himself or herself already? And secondly, that second part of the second statement with regard to the AI system is put in the active voice. If it's put in the sort of passive voice, it changes the whole game, doesn't it?
I'm sorry, what do you mean by the second part of the second statement? I'm not sure.
The second statement says that the AI would do no harm to itself or should prevent a person to do harm, or people to do harm to themselves.
Or through inaction allow people.
Or something
no,
like
it's
that.
Through inaction allow people
Right.
to come to harm.
But since people have free choices, doesn't that second statement suffer from some degree of uncertainty in the first place? And also, if you put the second part of the second statement in the passive voice, then it becomes a problem, doesn't it?
Yeah, well, so let me just say, so Asimov didn't intend his laws to be watertight. He intended them to have holes so that he could write stories about the robots doing weird things. Right? And he certainly didn't prove any theorems. But in what we're trying to do, we actually do prove theorems. But all theorems, right, whether they're theorems about computing devices being secure or communication protocols being secure, or bridges not falling down, or AI systems behaving themselves, they're all based on assumptions. And the question is, do you trust the assumptions? As you weaken the assumptions, you have to make the system more complex and more robust in order to still satisfy the theorem. So the theorems we want are that the machine is provably beneficial to the human. And the biggest assumption is, of course, what do we mean by human, right? What are the properties that we have to assume about humans in order to guarantee this theorem? And it's early days yet.
I think we have time for one last question.
Oh, no.
So I'm afraid to ask this question, but kind of like, I mean, the thing I'm kind of curious, because as we're doing the presentation, you're talking about how you change the thing to make it better. And the kind of last I remember is to change to say, instead of meeting their objectives, meeting our objective. But to me, it seems like humans are not really that great at stating what the objective really is. I mean, just take any example, go to any company. A lot of times we have conflict between the leadership team and the employees about not clarity in objectives, or given conflicting objectives, right? There's all these books written about management style, tyranny, the employee only want to be only one objective. The management say, no, you need to do A and B, not A or B. So I mean, they try to achieve our objective. I'm not sure we're that good at stating what the objectives are. I mean,
I
think we are. Humans are not very terrible at stating what objectives are.
Okay, so
even for one person, but when you have multiple people, then it gets more complicated. So.
So the whole basis of this is, in fact, that we cannot state our objectives correctly. Because if we could put them in the machine, and we can't. But we still have objectives, right? In the sense that we have preferences about the future. If I could show you two different futures, you could say, well, I like this one, or I like that one, or actually I don't mind which it is, right? So the trick is how to infer those preferences from behavior. And I think maybe something underlying your question is a thought that occurs to many people, which is that some human objectives are undesirable.
No, I mean, just I don't want to be too offensive. Like today, humans just irrational in this sense. Just give one example: is people want to eat whatever they want, but when they get sick, they want to be taken care of, and they're really conflicting objectives, right? And that's why people say, well, healthcare for all should be free, but then they don't talk about human responsibility for taking care of their own health, right? So I think.
Yeah. So there's right. So eating too much cake, right? And then regretting it is an example where we're making decisions that don't reflect our own preferences, right? But I mean, even, so Lee Sedol, right? So Lee Sedol is a Go player who lost to AlphaGo, right? And he lost because he made moves that guaranteed he was going to lose, right? Now, you don't want to look at his behavior and say, oh, I guess he wanted to lose because he made these losing moves, right? No, you want to say he wanted to win, but he wasn't smart enough, right? And we are not, right? So we're not smart enough to resist the cake, right? But it doesn't mean that we want to turn into Oompa Loompas, right? It just means we have weakness of will and we're making decisions on short horizon, which we later regret. And so AI systems should understand that and can maybe even maybe even gently remind you that you've had enough cake.
So this is a great segue. I'd like to thank all the panelists and invite you all to enjoy some cake outside. And thank you once again for coming, for your support, and thank you to Micron for hosting this event tonight. Go Bears, and I hope to see you all outside with the students. Thank you.